Okay, I hope I'm audible to all my students who are attending this particular lecture for the Econometrics course. In this particular lecture, I'm going to continue with the discussion of basic concepts in time series regression. The book I prefer to follow for my lectures on this particular module, this is Essentials of Econometrics by Gujarati and Porter. Okay, and if all students can recall that in the previous lecture we had started with the discussion of a stochastic time series process. So we said, first of all, we learned that a stochastic process has the variables which are ordered with respect to time. So when you look at variables, when you order variables with respect to time, that's called a stochastic process. It can be a continuous process or a discrete process, depending upon the variable, values taken by the variable. Then we had also looked at what is meant by stationary stochastic process. Okay, so I'm quickly revising the definition of a stationary stochastic process again with all students before we move forward. So let's quickly start with the discussion of this particular lecture. So I'm just writing, first of all, the main heading just for completeness. We are looking at time series econometrics. Time series econometrics. Some basic concepts. Okay. And I'm just writing the name of the book also, which I'm following for my lectures on this particular module. Formally, this is chapter 21 of the book Essentials of Econometrics. Essentials of Econometrics by Gujarati and Porter. Okay. Now I'm quickly revising from the previous lecture what is meant by a stationary stochastic process. So recall from the previous lecture, that a stochastic process, is said to be, STB stands for said to be stationary if its mean and variance are constant over time, and the value of the covariance between the two time periods depends only on the distance or the lag between the two time periods and not the actual time at which the covariance is computed. Not the actual time at which the covariance is computed. So when we talk about a stochastic process, it is said to be a stationary stochastic process if the mean and the variance of the random variable are constant over time. They are not changing over time. The value of the covariance between two time periods is only going to depend upon the gap between the two time periods and not the time at which the covariance is computed. Okay, if I erase all this off, I can just write this in mathematical terms also. So let yt be a stochastic time series with the following properties. with the following properties. You can see that the mean is expected value of yt, which is equal to mu. Variance is denoted by variance of yt. By definition, it is expected value of yt minus mu square, which is equal to sigma square. And the covariance is gamma k, which is expected value of yt minus mu times yt plus k minus mu. So I can say where gamma k is the covariance, gamma k is the covariance at lag. Clearly, students can see that since the mean and the variance are constants, and the covariance only depends on the lag between yt and yt plus k, which is k. The difference between t and t plus k is k only. So you can clearly see that yt follows a stationary stochastic process. Yt follows a stationary stochastic process. Okay, so this is where we had stopped in the previous lecture. Now, suppose suppose we try to shift the origin. Let's understand this intuitively. So if I erase all this off, intuitively, so this is what we are doing new in this lecture. Intuitively, suppose we shift the origin of the random variable y. Suppose we shift the origin of the random variable y from yt to yt plus m. Now, if yt is to be stationary, then the mean, variance, and the autocovariances are nothing but the covariances. The autocovariances of yt plus m must be the same as that of yt. So if I shift the origin of the random variable y, suppose I shift the origin from yt to yt plus m. If I say that y follows a stationary stochastic process, yt plus m should have the same mean and the same variance and the same autocovariance as yt. Okay, so I am explaining it further. In short, if a time series is stationary, then its mean, variance, and autocovariance at various lags remain the same no matter at what point we measured. No matter at what point we measured. That is, they are time invariant. They are time invariant. So when I talk about a stationary stochastic process, if you look at a time series process, which is a stationary time series process, the mean, variance, and the covariances at various lags are always going to remain constant. They're always going to remain the same, no matter at what point you measure. So they are invariant of time. They are not influenced by time. The mean variance and the autocovariance are independent of time. I can further elaborate that such a time series will tend to return to its mean. Such a time series will tend to return to its mean, and this is called mean reversion. This is called mean reversion. Such a time series will tend to return to the mean, and the fluctuations around this mean, which we call as the variance, the fluctuations around this mean, that is, I can write variance, will have, or I can say will be constant. Okay, so when we talk about stationary time series process, such a time series is going to return to its mean. Okay, and the fluctuations around this mean. Remember, variance is going to capture the fluctuations around the mean. These fluctuations around the mean are going to be constant. Okay, so now let's talk about the opposite side. Let's talk about what is a non-stationary time series. We have talked about a stationary time series, and if I sum up, a stochastic process is said to be a stationary time series process if the mean variance and the covariance are constant over time. And the covariance only depends on the time lag between the variables. Okay, so let's now erase all this off and let's talk about what is meant by a non-stationary time series. Non-stationary time series. Okay. Okay, so I can write if a time series is not stationary, that means if it does not have a constant mean or variance, or I can say a constant autocovariance, then it is called a non-stationary time series. It is called a non-stationary time series. In other words, a non-stationary time series will have a time varying mean. It will have a time varying mean or a time varying variance, or both. Or I can write both. So when I talk about a non-stationary time series, in case of a non-stationary time series, the mean of the random variable y will change over time. The variance of the random variable y will change over time, or both the mean and the variance will change over time. So this is the difference between stationary and non-stationary time series. In case of a stationary time series, mean, variance, and the covariance of the random variables are all constant over time. However, in case of a non-stationary time series, either the mean of the random variable will change over time, or the variance will change over time, or both will change over time. Okay, so hoping that all students have understood this. And now let's talk about a special type of a stochastic process called the purely random or a white noise process. So if I erase all this off, I can now write a special type of a stochastic process, namely namely a purely random. So I can write consider a special type. Let me slightly change my statement. I can write consider a special type of a stochastic process, namely a purely random or a white noise process. Okay, so I can say a stochastic process is purely random if it has zero mean, constant variance, zero mean, constant variance sigma square, and is serially uncorrelated. So students, this is important. We say that a stochastic process is a purely random process or a white noise process if it has a zero mean, a constant variance called sigma square, and is serially uncorrelated. Remember when we were doing simple linear regression, we had something called the population disturbance term UT. So consider the population disturbance term. Consider the population disturbance term UT from my lectures on linear regression. From my lectures on linear regression. Remember one of the assumptions we had made? Okay, one of the crucial assumptions was that UT is independently and identically distributed normally with mean, zero, and variance sigma. Recall from my lectures on linear regression, the population disturbance term UT is independent and identically distributed normal with mean, zero, and variance sigma square. That is, I can write UT is independently and identically distributed. It is independently and identically distributed as a normal distribution, with zero mean and constant variance, which is sigma square. Therefore, I can say UT follows a white noise process. UT follows a white noise or a purely random process. It follows a white noise or a purely random process. Why? Because it has a zero mean, it has a constant variance equal to sigma square. And we had just learned that any stochastic process is said to be a purely random or a white noise process if it has a zero mean and the constant variance. From our assumptions from linear regression module that UT is independent and identically distributed following a normal distribution with mean, zero, and variance sigma square, it is a purely random or a white noise process. Okay, so students, this is where I stop in this particular lecture. We have completed our discussion of a stochastic time series process. In the next lecture, I'm going to talk about the types of non-stationary stochastic process. So I'm going to dig deeper into non-stationary. Today, I've just looked at the definition of non-stationary, but what are the various types of non-stationary stochastic process is what I intend to look at in the next lecture. So the next lecture is going to be a very important lecture. We are going to focus on non-stationary stochastic process in the next lecture. So I hope our students have enjoyed this lecture. Any doubts, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolof economics@gmail.com. This is where I stop in this lecture.